This is Astrophysics, this is Cosmology Lesson 5, this is last one, Dark Energy Controversy and Quasars. So in 1998, astronomers discovered that a very distant Type 1a supernova, again the white dwarf supernova where it accretes too much mass, goes over its, in a binary star system, over its critical point. The supernovas were further away than expected. A measurement of their redshifts, which is obviously used to measure their recessional velocities, and the use of Hubble's law to obtain their distances shows that these supernovae were fainter than expected. So these measurements indicate that the universe is expanding faster at this moment in time compared to when the supernova exploded, as the light has taken such a large amount of time to reach here. So it's travelled further to reach us than expected by a constant rate of expansion. And that's assumed to be the case with Hubble's law, that the rate of expansion of the universe remains the same. So these and further measurements have led astronomers to conclude that the expansion of the universe has actually been accelerating for about the past 5 billion years. So before this discovery, the expansion of the universe was expected to be decelerating due to attractive gravitational forces between the galaxies on each other. So there appears to be some unknown repulsive force acting, which is releasing some kind of hidden potential energy, which is currently known as dark energy. So the nature of dark energy is unclear. It's thought to be a form of background energy present throughout space and time. It's more prominent than gravity at large distances, as gravity obviously follows an inverse square law, so it becomes weaker, whereas the force associated with dark energy is thought to actually remain constant. So current theory suggests that it makes up about 70% of the total energy of the universe. And the idea of dark energy leads to the speculation that in the future, the force associated with dark energy will ultimately tear apart all gravitationally bound structures, including galaxies and solar systems, and eventually could overcome electrical and nuclear forces to tear apart atoms themselves, ending the universe in a big rip. Sounds really nice. Dark energy controversies. It's been noted that if Newton's law of gravitation became GMM over R at large intergalactic distances, then the acceleration of the expansion of the universe no longer requires the existence of dark energy. So other alternative ideas for dark energy have come from string theory, brain cosmology, and the holographic principle. Holographic principle is quite a bizarre one. It states that the universe is like a 2D, on the outside of a 2D sphere, and then projects reality into a 3D space, which obviously sounds ridiculous, but some supremely intelligent physicists have proved that mathematically. If you want to look that up, holographic principle, it's a weird one. Right, so let's look at quasars. So quasar stands for quasi-stellar radio source. It's a compact region in the centre of a massive galaxy surrounding a central supermassive black hole. Remember that we believe that these supermassive black holes at the centre of galaxies. So it's about 10 to 10,000 times the Schwarzschild radius of the black hole. Remember, we calculate Schwarzschild radius using 2gm over c squared, basically the escape velocity equation from gravitation. The quasar is powered by an accretion disk around the black hole. So quasars is first identified as being high redshift sources of electromagnetic energy, including radio waves and visible light, that are point-like, similar to stars, rather than extended sources similar to galaxies. Quasars are among the oldest and most distant objects in the universe, and they're characterized by very powerful light output, much greater than the most massive stars, so it's a very low absolute magnitude. Negative by low I mean negative values. Relatively small size, it's not much larger than a star, and a large redshift indicating distances between 5 and 10 billion light years away. The first quasar discovered, which was 3C273, produced very strong radio emissions. However, not all quasars produce radio waves. Right, so let's finish with a recap calculation question. And why not? Everyone loves calculations. That's why you did physics in the first place. So let's have a look at this one. Light from a certain quasar was found to contain a spectral line that has been redshifted by 80 nanometers from its normal source wavelength of 486 nanometers. And what we're going to do is calculate the recessional speed of the quasar. So you need Doppler shift equation, so it's change in wavelength divided by source wavelength equals V over C. So really straightforward. So the change in wavelength is 80 nanometers divided by source wavelength 486 nanometers equals V over C. So we need to do that ratio and then times 2 by speed of light. So the ratio is 0.164, so this is going to be travelling really quick. Multiplied by speed of light, 3 times 10 to the 8, and that gives us, it's actually 0.165. That's me not being able to round up. Anyway, we use full value, times it by speed of light, 3 times 10 to the 8, and it gives us a mammoth 4.9 times 10 to the power of 7 meters per second. Alright, hopefully you found all that useful, and if you're watching the playlist, that's the final astrophysics lesson. And good luck in your exams. Thanks for watching.